Okay, so we're here in chapter 5. Now chapter 5 is usually a bit of a doozy of a chapter. It's not very long, it's only 3 sections, but we throw a lot of new information at the wall here. Some of it is going to feel familiar, some of it's going to feel very foreign, especially when we get to section 5.3 and we start talking about Poisson distributions. But essentially chapter 5 is a study of probability distributions, different types of probability distributions, and what we do with them and why we choose the ones that we choose. So we're going to start in 5.1 with introducing what's called a discrete random variable. So we have 4 objectives in this section. The first is to define random variables. The second is to define discrete probability distributions. The third is to talk about something called expected values. And the fourth is to look at variance and standard deviations. Of discrete probability distributions, and I'm going to abbreviate this as DPDs. So this is that DPD. DPD is not an official abbreviation, it's just something I'm going to do to keep the writing down a little bit, this initial thing. So let's define a probability distribution. We've just spent a whole chapter talking about probabilities, how we find them, what we can do with them, answering questions about probabilities. So, a probability distribution, these list probabilities first and foremost, not frequencies. So, we saw frequency distributions in chapter 2 and 3. Now we're talking about probability. So, everything that you list in your probability distribution is a percentage. It's a probability, it's a chance. And so, each probability, in the distribution is some value. Now, there are 2 classic rules to probability distributions. The first is that all probabilities are between 0 and 1. And we have a special probability function, as it's called, in statistics and in math. And so the symbolic representation of this is that we have 0 less than or equal to the probability of capital X equaling x sub I less than or equal to 1. Now we will get into what this capital X and little x sub I are in a second here, but this just is the symbolic way of saying exactly what this says. It's all probabilities are between 0 and 1. In statistics, capital P in math in general, capital P, unless you're talking about functions, polynomial functions, capital P is probability. This is the probability that capital X equals x sub I. So all our probabilities need to be between 0 and 1. Secondly, the sum of all probabilities is 1. And our symbolic representation here is capital sigma P of x equals x sub I equals 1. So if we add up all the probabilities in our distribution, it has to equal 1. And we know that our probabilities from our chapter 4 rules, the only set that we'll ever see, the only thing we'll ever see of having a probability of 0 is going to be an empty set. And the only thing that has probability of 1 is going to be the entire set, or the entire distribution. All right, something has to happen, but we don't know what that thing is yet. So, let's talk about random variables here. So a variable whose numeric value is determined by the outcome of a probability experiment is denoted as a capital X. That's what this capital X here. So we say this, we use capital X instead of a little x because we're saying that this isn't a truly unknown quantity and there's some sort of probability experiment that has to be run. Now I want to be clear here, probability experiment is not an experiment in the classical sense where you run an experiment and see. A probability experiment can be hypothetical or it can be real. A real experiment where something is run, data is collected. But thinking about, we've used the card drawing example a couple times in different sections, that's a probability experiment. It's a completely theoretical experiment where we can still study it and understand all the outcomes from drawing cards from a deck of 52. Now, a discrete random variable is a discrete random variable that can have a finite or infinite number of possible values. So this is finite or infinite number of possible values determined by some counting process. It's still a random variable, so you still denote it as capital X, but this is the important change. It is finite or infinite. Now, mathematics at one level can be broken up into two camps, essentially. You have discrete mathematics and you have continuous mathematics. Continuous mathematics is things like calculus and differential equations. Discrete mathematics are things like statistics, numerical analysis, probabilities, of course, coding and algebras to a certain extent, but there's some overlap in algebra. Obviously, calculus deals with a lot of functions, and so does algebra. So when we're talking about discrete random variable, we are in that latter half, where we have a finite or infinite, but they're counting processes that are determining how many things are there, which means even if it's infinite, if any of you go on to ever take a discrete math class, you'll learn, or a set theory class, you'll learn about something called countably infinite. Countably infinite is what we mean by discrete here. Is that even though it could be infinite, you can still count up, theoretically count up, all of your outcomes. And if you're trying to reconcile what countably infinite is, think about integers, our counting numbers, 1, 2, 3, 4, 5, etc., etc. The integers go on forever. They are truly infinite, but you could still count and say all of those numbers. We have names for all of them, and we have digits for all of them. So that's what it means to be countably infinite as a base definition, is you can count them using the integers, the positive integers. So moving on to the next definition here, discrete probability distributions. This is a probability distribution for a discrete random variable. And it's as simple as that. So it's a probability distribution for that discrete random variable. And one thing I will say here to kind of connect these two things is you can think of discrete random variables as sort of like events. From the previous chapter. So discrete random variables have a potential set of outcomes to them. That potential set can be finite, which is the classic event that we studied in chapter 4, where we have a certain number of things and we see out of all the outcomes. Or it can also be infinite. That's why I say it's sort of event-like. It's not quite like an event, because an event in the classical sense has to be finite, unless you're thinking of the one that encompasses your whole set, your sample space, but that's not what we're talking about here. So let's look at a discrete probability distribution. We're going to construct one for the, and these are necessary for x, the sum of two dice rolled. So one of the practice problems I said you could try out is listing all the dice outcomes. So if you roll two dice, we're just going to list out those outcomes. You can get a 1 and a 1. That is going to be a 2, because that's the sum. You can have 1 and 2, which will be 3, 1 and 3, which will be 4, 1 and 4, which will be 5, 1 and 5, which will be 6, and 1 and 6, which will be 7. Now I'm going to actually list out all of these outcomes here. So if you didn't do this, this is a good opportunity to pause the video here and try and list out all your outcomes, and you can check your work. But the reason I'm going to list these out is because I need to count them. If I'm creating a probability distribution, I need to know all the possible outcomes so I can count up their percentages. So I'm not going to narrate over this too much. Just know I'm listing these things out. So just to explain a little bit, these are all the outcomes after I roll the dice, but remember, we're looking at the sum specifically, so like I did in the first two lines, you need to add up all of these things, and so that's what I'll be doing now. There is an interesting pattern that appears, you may have noticed it as you're doing this, and you can see it now, hopefully going down the list of sums as I write these. They're just counting up by 1 exactly, and that's just because of how I organized this. I've done this a couple times, so I know how to make that pattern appear. So the reason we need all of these is when we create our probability distribution, sum of 2 dice rolled, we have our little x, and then we'll have the probability that any given roll, capital X, the discrete variable, is equal to x. So this little x is the possible sums. So we can have 2, 3, 4, all the way up to 12. That's all the sums that we can get when you roll 2 dice. And so now to get the probabilities, if you remember, the total number of outcomes here is 36. 6 times 6, 6 options on one die, 6 options on the second die. Multiply those options together, 36. And then you just have to look at how many times your possible sum appears in your data. So there is 1 out of 36 here, 2 out of 36 here, 3 out of 36 here, 4 out of 36 here, 5 out of 36 here, 6 out of 36 here, and then it drops again, 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36. So this table here that I've now constructed, this is our probability distribution. It tells us the potential outcome and how many times or its probability as a percentage of how many times it appears out of the total. Now I didn't simplify any of these just because I didn't. Typically these will be simplified, you know, 1/18th and 1/12th and 1/6 and things of that nature. I just didn't simplify them. Now you can check that you did this right, which is the nice thing about probability distributions. Just add up all these numbers. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. If you add all those up, remember the sum, x equals little x, we know that that's supposed to equal 1. So if you add all these up, what we actually get is 36 out of 36, which equals 1, or 36 over 36 is what I should say, which is 1. So we know we've done it right. So that's the nice thing about probability distributions. You have a built-in check by this second rule from that first page. You're supposed to add up to 1. So this is the basics. forming a probability distribution. Obviously, this gets tedious, just like forming frequency distributions or listing outcomes. It's not something that you want to be in the habit of doing all the time, but for relatively small experiments, we can list out the outcomes. So for expected value, the expected value for a discrete random variable capital X is equal to the mean of the probability distribution of X, and is given by the following. So our expected value is capital E of a variable, discrete variable X. This is our mean, our mu. And this equals the sum of all X sub I times their probabilities. So in the next example, we're going to work this out. But again, I'm talking about abusive notation once more here. We're using mu. We saw mu is the population mean for a frequency distribution. Mu is the expected value or the mean of a discrete probability distribution as well. So now let's take this formula. Oh, I forgot. I have blanks here where X sub I is the ith data value of the random variable X. Remember, these are the data values. These are the probabilities. So it's just like with your frequency distribution, you have classes and then you have frequencies. We have data values and we have probabilities. So we're going to calculate the expected value of the sum of rolling two dice in this next example. So we just apply this formula. So we're summing up all of the multiplications of a data point and its probability. So our expected value, which is our mean, our mu, is 2 times 1 over 36 plus 3 times 2 over 36 plus 4 times 3 over 36. So all I'm taking is the data value and its probability and multiplying and then adding them together. Now I'm not going to write this all the way up, but you keep doing this all the way till you get to the end. 11 times 2 over 36 plus 12 times 1 over 36. And you work this out in a calculator, multiply everything out, add them all up, and what we get is 7. Well, this actually makes sense if we look at our data. So looking at our data here, 7 has the most opportunities. And if you think about two dice, 7 has the most faces that you can roll the first die and still be able to get to 7. And so what I mean by that is, think about it. You roll a die, you get a 1. You need to roll a 6 to get a 7. But to get a 2, you have to roll just another 1. To get a 3, you have to roll just a 2. Let's say you roll that first die again, you roll a 2. Well, you need to roll a 5 to get a 7. But you've now eliminated getting a 1 because you rolled a 2. You've also eliminated anything higher than 8, so 9, 10, 11, 12. If you roll a 3, you need to roll a 4. But now you've rolled a 3, so you've eliminated 2 and 3, and you've eliminated 10 or higher. If you roll a 4, you just need to roll a 7. Or, I'm sorry, you need to roll a 3 to get that 7. But again, you've eliminated getting 2, 3, 4, and 11 and 12. If you roll a 5, you just need to roll a 2 on the second one. If you roll a 6, you just need to roll a 1. 7 is the one number that every single face of a die can combine with another face to make 7. Whereas certain of these only have very limited combinations. Their probabilities are very low. There's only so many chances. But all 6 of your sides of your die have a pair, a partner, that adds up to 7. And so it makes sense that 7 should be our expected value. Does that mean you're going to get 7 every time? No. It just means if you roll, let's say, 36 times, you should roughly get a 7 most 6 out of the 36 times, okay, probabilistically speaking. We're going to do more with expected values here. So let's do this example with expected values. Suppose Jay is betting their friend on a football game. For every kick the kicker makes, they will pay their friend $30. Seems like a good deal for the friend. For every miss, the friend pays Jay $40. So he's trying to grease the wheels a little bit here, get him incentivized. Going into the game, the kickers made 18 out of 23 kicks. So in part A, what is the expected value of the bet for 1 kick? And for part B, what about for 4 kicks? And same question, what is the expected value for 4 kicks? So what we need to do is look at the probability distribution. And technically this is a discrete probability distribution. So we have our bet, we have our x, and our p of x equals x. So the x is the dollar amount, -30 and +40. Now we're thinking this as Jay's bet. Now we could have flipped these, it wouldn't have mattered. Written the 40 here, written the -30 here. The probability that he loses the $30, that he pays them, is the only probability that we were given, 18 out of 23. The probability that he makes the $40 on the next kick is what's left, the 5 out of 23. Because those are the odds. If you've ever thought about or heard about sports betting in movies or something, TV, you hear about odds. These are the odds. So 18 out of 23, those are the odds. You would convert that to a percentage, and that's the percentage you'd be given. So the expected value then is the sum of the odds, the probability, times the data value, and then add it to the next one. So it's -30 times 18 out of 23 plus 40 times 5 out of 23. And you add that up in your calculator and you get -340 out of 23, or roughly -14.78. Remember, it's dollars, so we're rounding to the second decimal place. So on average, Jay should expect to lose $14.78 for each 1 kick bet. Now this is weird because we look at this and we go, well, it feels binary. You either win or you lose. But the probability of losing is higher. But if he wins, he earns more. So the expected value is going to reflect that. It's not quite half, and that not quite half is because he can earn more if he wins. So if he were to bet 23 times, he should probably be down or have lost a total of $14.78. Now that's not quite accurate because we rounded, but that's the idea here, is probabilities always look at the overall, the over-encompassing. So I know I'm a little over here. We'll finish up this example and then I'll do the last bit on standard deviation and variance in another video. But for part B, if we're doing 4 kicks, we just take 4 times the expected value of 1 kick, because now he's betting on 4 kicks. So what we mean by this is he's saying, okay, I bet you for 4 kicks at a time. Well, 4 times -14.78 is going to be -59.12, and this is in dollars. Again, I'm rounding to the second decimal place. So if he bets on 4 kicks up front, he says, okay, we're going to bet on the first 4 kicks after these initial 23, he should expect to lose a little under 60 bucks. Okay, we'll pause here. We'll come back. The next bit is a little bit longer, so I don't want to get into it here since I'm already at 25 minutes.